Okay, in this final section of chapter 14, we're going to look at some more advanced convolutional neural network architectures and apply them to the Caltech 256 image database, which is a little more challenging, kind of a fuller set of data of images that we can look at. They're larger, the color, and there are more categories, a little more challenging. Um, just a quick overview of those images, the Caltech 256 images. There's also a Caltech 101 images. It's a database of 256 categories of images, and there are about 30,000 images in each one, and they range in pixels from about 150 to 150 pixels to about 600 pixels. We'll be working with images that are about 250 pixels by 250 pixels, that sort of size. Here's some samples of those images here, and they're broken into categories. So like one of the categories is dogs. Here's we're reading in the images that I've pulled from Caltech, and here is a sample. Here's a bunch of dog images. These are just small samples of these, but each one of these is a pretty big image of dogs. And here's another example and this is ferns and different images of ferns. And so the idea is that you want to create a model that will recognize, if it sees an image, recognize it right, which one of 256 categories there are out there: dice, ferns, animals, cars, automobiles, whatever that are out there. So we set up our callbacks. Again, we'll learn more about this when we return back to Unit 10 and 11 in our database, but this will help motivate us and understand why we want to do this sort of stuff. And let's jump into our textbook. Well, no, let's not do that quite yet. So here we're going to read our images. What happens now is when we run this, we load up all our images. So our images are loaded from GitHub into this folder, the 650 image database. And there's the Caltech 20 images. Now, rather than doing the whole 256 image database, I've just selected 20 categories for us to try. The entire database is quite large and would have trouble. We're already filling up almost half of the disk space with this. So we couldn't necessarily load these all into this Kaggle environment, this Colab environment. So I've selected 20 categories for testing and training. And so in each category, there are images, and so there's a bunch of images of cowboy hats and a bunch of images of crabs and dice and that sort of stuff for this. So in each of these categories, there'll be a bunch of images of that sort of category. So these are broken up into folders. Each folder is an example of a different category. And so this is how Keras likes images, and they have a special functions called flow from directories that'll load up these images and train these images, because all these images couldn't fit in the memory. When we're working with minced database with just the images, all those images actually can be loaded up and used in memory, but this image is just too large. So what we do is specify the folders where these images are at, where the categories are at for the training and the testing data. And then we create these routines that will go out there, load up an image and do things for it. And in our case, we're just rescaling it. Our neural network with images, the values are between 0 and 255, but neural network prefers an image, inputs between like 0 and 1. So we rescale this by dividing all of the pixel values by 255 here. You can also do things like rotate and flip the images, that sort of stuff, but we're not doing those here. And again, we do the same thing for our test and training validation data here for this. So we set this all up, and then we'll set up and train our neural network here. So again, we have our layers, convolutional, max pooling. We'll also possibly add up a dropout layer. We'll talk more about this later on, and another type of dropout layer for CNNs. But again, if we're overfitting our database, if our training data fits real well, but our validation or testing data does not, we sometimes add some dropout layers and do that. And again, we'll return and talk more about this later. There's also, again, here's the spatial dropout, which is a different dropout just for CNN layers, flattening, and a dense layer. So those are our kind of layers we have to choose from. So we set up our network here. So we have our output. We have 20 different categories. We set up a sequential network. We start with 8 layers with 3x3 kernel. We do max pooling, 16 layers, max pooling, 32 layers, max pooling. So again, not too many layers here, 64 layers and max pooling, and then we flatten, have a dense layer with 256 nodes, and then an output, which is again 20 nodes here. So here we can kind of look at that. Our images start here. In this example, since our images are so big, we're not doing padding. So we start with images that are 224 by 224, and after our first convolution, they're 220 by 220. We then do a max pooling, drops them in half. We do a filtering, and again, we lose some of the edges, so they're down to 108 by 108, but that's okay. We still have pretty big images. We do a max pooling, they're down to 54. We do a convolution layer, another max pooling, we're down to a 26 by 26 images, a convolutional layer, now we're up to 64 filters. Finally, max pooling 12 by 12. And I often find this is a good range when you get your images down to about 12 pixels, or between the 10 and 20 range of that. All right, sorry about a little break there. My cat is joining me, so if you see this tail, I'm still recording at home even though it's summer of 2021. Okay, sorry kitty. Okay, so we've got our pooling layers here. We're down to a 12 by 12 with 64 pixels, and then we end up with a flattening layer and a dense layer here. So we end up with a pretty large network, almost 2.4 million connections that we're working with. So this is, again, a much larger network. It'll take longer to train, so you can run through the training here for this and see how accurate you can get for this stuff. And watch not only the accuracy of the training data, but the accuracy of the testing data. Okay, and again, we can plot our training history, and again, our accuracy will get way up here. Here I'm running it for 50 epochs. It looks like I wouldn't have to run it for that long. Probably 20 epochs would have been enough here. But my validation accuracy, again, doesn't get so high, only about 80%, because those are images it's never seen before. So it's never seen that picture of a dog, and so it's not as good, where it basically memorizes all the dog pictures and all the fern pictures. Gets up to 100% accuracy on those. And again, dropout layers sometimes will help increase this validation accuracy up a little bit more. Okay, so you write up, talk about this, answer these questions, make some changes, try to do some adjustments, go up here, maybe add more layers. We don't have many layers here, many filters. We only have 8 to start with, and then 16. Often we will start with like 32 layers here. Sometimes we'll have, rather than just one convolution layer, we'll have 2 convolution layers here. Decide what other changes you might want to try. Maybe see if you can figure out how to add a dropout layer or something like that. Make one change to that and report your results in the write-up. Okay. Now, the next stage is to look at some pre-trained network, because a lot of researchers have been doing this, adding layers, trying different things out for the last 10 years while convolutional neural networks have been out there, and have devised lots of different layers out there. And so let's look back to the textbook. But the textbook will start talking about CNN architectures here and how they're set up. So they talk about the basic layer, but then they talk about Google's LeanNet structure that was started, and so it had inputs and a convolution layer, a pooling layer, convolution layer. Again, it started with 6 filters, went up to 16, and then went up to 120. Different sizes of kernels, 5 by 5. The max poolings were 2 by 2s there. So that was the first set, one of the first ones. AlexNet was a different CNN architecture. that was run on this, what is called the ImageNet data set, and did very well. And again, they talk up there. Now, I always think the textbook lists this in reverse order. They list the input out here and the output here, where when we look at our network structures, it's always the opposite. So the network, let's see if I can get up here, past all this training. This is always the output at the bottom and the inputs at the top. Start with the large image. So just be aware that the textbook lists the input down here feeding upwards. So again, different convolutions, some 3x3, some 5x5 layers here. And then the size of the images, they started with 55 by 55 pixel images. They dropped down to 27, 13, and ended up with 6x6 images. And they had 256 maps or filters here. You can read a little bit about that, and then some other ones. But again, people have been working with these different networks for quite some time. So Google's LeNet architecture was developed in 2014, and that had much more complicated structures. Rather than just one filter sequentially feeding into another filter, they'd have one layer feeding into a number of different types of filters, 1x1 convolutional filters, 3x3 convolutional max pooling filters, 5x5 filters. So they broke it up into lots of different types of filters and a couple different layers, and then they brought these all together into one large filters output. So they created these what are called inception models here. And then they would stack these models. Each inception module was made up of 9 filters, or 9 layers, all stacked together in a complicated way. And again, we'll look at how to do this later on, but we'll use that sort of stuff now. So it talks a little bit about that network here, and then here's the structure, input, convolutional layers. So they do a couple normal convolutional and max pooling, and then they switched into these inception layers here with these complicated. So this Google LeNet uses these inception modules that went through here, and finally a dropout layer and a fully connected 1,000-unit layer, and then a softmax output layer. So this is a huge network structure. We're getting into some large network structure. So the book goes through and talks to you about some of these different network structures. VGGNet was developed again in 2014 and was a similar structure. ResNet had an interesting structure where they had these networks where they had a couple layers, but they also had a connection from the input straight to the next layer that would skip these layers. And so this layer would actually look at some of the complicated features and the basic features from the previous layer and combine those with this, what is called a skip connection. Okay, so how are we going to use this? So in our next layer here, so for task 5, we're going to use some pre-trained neural network models. So there, besides your book, there's a couple articles here that also describe some of these network structures that I thought you might want to look at. But Keras has a number of pre-built networks in Keras. These include the inception layer. So we just looked at Google's inception, what's called V1, the LeNet, but there's been since inception V2, inception V3, mobile nets, which are trying to optimize memory for mobile phones. ResNet, we just talked a little bit, the textbook talks about that. And then ResNet version 2, VGG16, VGG19, which was made after VGG16, and the exception module. So here's what we can do. We can create our network this way. We specify an output size, and we specify one of these modules. So like here, we're using VGG16. So we're going and loading in the VGG16 network. Now, if I wanted to use, like, say, the inception V3 network, I could, let's comment this out. So remember, the pound sign are comments here. And so everything that starts with a comment with a pound sign is a comment and ignored. So I'm going to now use this one. So where I was using VGG16, I'm now using Inception as my network. But I was using VGG16 before. So you specify that. Now, we also use pre-trained weights with this large data set called ImageNet for this. And we don't include the top part of the network. If you remember these networks, a lot of them start with inputs, feed forwards, and then the top part of the network here is often a couple fully connected networks and an output layer. And so when we say skip the top, it'll drop out this stuff, just have the convolutional stuff. And so then we can take that and we can add our own top network. So we're going to do a global average pooling layer, which is kind of like a flattening layer, and a dense layer to do our output. And sometimes we can add a couple layers, like it's not uncommon to add a couple dense layers with like 1,000 or more inputs in here. So sometimes you'd add another dense layer in here, right, like there. But we don't necessarily have to do that for this. So we specify our networks. All right, we create our sequential network is made up of our pre-trained model, and then we add on a global pooling and our dense output, and then we do our summary. So our summary is actually going to show two things. First, we'll do a summary of the pre-trained model. So this will show, let's see, right now we're using VGG. So it starts with VGG 224 by 224 image, and we filter it down, we add more filters, now we're down to a 14 by 14 image with 512 filters and 7 by 7, 512 filters. We end up having 14 million connections in that. But these are all pre-trained, none of them are trainable here. And then we add onto that our network, which is just the VGG network plus our stuff. And so we end up adding 10,000 layers, and that's the only part we're training with our network. So then we're going to fit this and run this and see how accurately you're doing. So your job then is to try out some different models. Oops. Describe this database, and then again, select a different pre-trained model, describe what it is, count how many layers it has, or estimate that. I'll just warn you, you may not be able to count them because, again, some like VGG16, you can go back here and you can count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. through this, and it's not too bad. Inceptions and some of those layers will have almost 100 different layers because they have inception models which have like 9 different filters in each model. So if you need to just estimate that. Okay, and run that and train that. So that's, here we're using this pre-trained model, and again, that's using some of these models that are described in this part of the chapter. Now later on in the chapter, they do talk about how you can actually build these layers here. So they talk about implementing the ResNet architecture with this. And in order to do that, we need to create non-sequential layers because, again, in these sorts of more complicated networks, not everything feeds directly into the next layer. And so, again, we're not going to go over this now, but we're going to then return back to earlier chapter 10 where we talk about how we might connect layers that aren't sequential. And this is our motivation for doing that. To make these more complicated CNNs, we need to be able to do things like that for this. Again, this talks about using these pre-trained models like we're doing and something called transfer learning, which is what we're doing now. We'll talk about some issues with transfer learning, especially with bias that can creep in depending on what learning was originally done with the original model. You might introduce some bias. So maybe your facial recognition system may not be able to recognize diverse faces if it was not, if you're using transfer learning and the original database was not built on on a diverse data set. Okay, so again, much of this we're not going to be able to talk too much about it. So these CNNs can also be used to not only label an image like saying this is a dog or whatever, but actually try to highlight a box around images in the screen in what it is. So we might label this as the iris flower, but this is our prediction where the CNN will think the flower is, and it'll learn to draw boxes around faces and things like that. You may have seen maybe online face definition systems that'll draw a box around your face, and that's using CNNs here. So again, we're not going to be able to go into this too much with these sorts of networks. So this is some areas where you could do more research later on with these more complicated neural networks and how they work and how they're set up. So again, much of this module we're going to have to skip here and do. So just to go down to those pre-trained networks and do that. And if you want, you feel free to read ahead to this if it's just beyond what we can do for these. So this ability of a network to segment, take an image and segment it and identify where there's buildings, where there's sky, where there's a person, where there's sidewalk, road, cars. CNNs can be used to do that sort of stuff. But it's kind of beyond the scope. And we'll actually look at a new, later on at a new type of network which not just categorizes images, but takes an image and generates a new image based on it. And so later on, we'll get back to this sort of creating an image based on another image. So, well, I hope you enjoyed this. Network is some of my favorite stuff to get into, so sorry the videos were so long.